So I'll be talking about kinetic tomography, spiral structure, and the Perseus illusion. Slightly provocative title, I'll admit, especially in the illusion context. A lot of this is work by my current graduate student, Carol Chernyshov. We'll be taking a postdoc to work with Jeff's work at University of Washington, and also a lot of work with Eddie Schlafly. Gail was here as well, but I show these guys' faces because they're on the job market. If you haven't already figured out, I talk really fast. Also, thank you, NSF. I talk really fast, and I leave very few words on my slides, which is a terrible combination. So I leave at the top of my slides everything you need to know about the slides, so you can check your email and then just look up at the top of the slide and kind of ignore everything I have to say. So that is how I would suggest you consume this talk. Okay, very good. Let's move forward. This is what I did for my thesis. I'm not going to talk about it all, but it's so pretty I have to show it in every talk. Okay, great. So from an astronomy perspective, spiral structure, right, is this unification. It's this intersection between star formation and galaxy formation. You know, if you really want to understand what's going on in our galaxies, especially in our disky galaxies, you want to understand what's going on with the spiral arms. And obviously, some people sort of define a spiral arm as where stars are forming. And so it's this wonderful place to work when you want to understand how to get at formation. But from a physics perspective, this is how you get at formation. This is the integral of the continuity equation, and this is how much mass there is in some kind of volume, and how it changes over time. And to get at that, what you need is some kind of sense of what the density field that we say interstellar medium is, and the velocity field. And never mind that the decadal 2020 white papers that I'm sure you are all probably writing right now don't have any kind of thing for the interstellar medium as a topic. Not that I'm butthurt on the topic, but anything that exists in the universe came from this process. Okay? And so if you really want to get at how things are formed, star formation, galaxy formation, what you want to get at is where the things are and what is their velocity field. We'll come back to this in a minute. So let's return to spiral structure. So a thing we might want to be interested in is how do spiral structures form? And luckily, people have been thinking about this for a very long time. This is a diagram that's a little bit hard to read from Roberts et al. Actually, just Roberts, 1972. And I'll just walk you through it. So here are some concentric radial rings. Here's the galactic center. And then here is where the spiral arms are. So this is this two-arm spiral shock model. And the point that was made in this paper is that you can build up these nice standing wave spiral structures, like Shu all taught us in his, I believe, undergraduate thesis. But the velocity field, if you have a spiral arm that's moving, after a while you're going to get a situation where the velocity of the interstellar medium coming into that arm is much faster than the sound speed in the interstellar medium, and so necessarily you'll get shocks. And so that's what this paper is all about. And so you see these streamlines where you have a flow that goes into the spiral arm, provides a shock, moves along the spiral arm, and shocks on the next spiral arm, and so forth. So you can solve these equations, and you can get something that makes sense. And this has been foundational for our understanding of how spiral arms work. Okay. And it passes some tests. So this is called the two-arm spiral shock model. And early on, people went and observed places where they thought they were seeing this two-arm spiral. This is MED1 here. I think this paper is by a theorist, and you can tell because the solid lines here are the theory. The really faint background lines are the observations. But you can see that they match pretty well. And so here they're matching in detail. You're actually matching the velocity field as they're going into the spiral arms. And you really reproduce this picture. So this is a paper from 1980, 8 years after that 1972 paper, and Frank Shu is still talking about this in 2016. This is something that we believe is telling us something about at least these kinds of galaxies, where you're having these incredibly strong interactions. So MED1 is going through a strong interaction. You see something similar in M51 as well. You need to have nearby galaxies here, because you need to be able to have lots of velocity resolution elements across between these spiral arms, and here it's even kind of marginal. But this really gives you an idea of that these two-arm spiral shock models are at least reproducing some of the details of the observations. But I would be remiss to say that this isn't still being talked about. Here's a classical look at what we might think our Milky Way looks like. And I'm mostly going to be talking about the Milky Way during this talk. You got some kind of bar, you've got these shallow pitch angle, sort of 12-degree pitch angle spiral arms that can wrap, sometimes more than once, or at, yeah, 1 point, whatever that is, times. So you see some significant, long spiral arms. And one thing, so first of all, everybody plots these 8 million different orientations. You can see publications where the sun is at the left, east, north, south, west. I'm going to try to put them all on the left so we can be consistent here. But if you look at these tangent points, one argument that Jacques Vallée has made is that you see this sequence of different kinds of tracers consistently as you look at these different tangent points. So if this is where the arm is, where you see all of the molecular gas, you see a sort of a shock from the hot dust lane in the front, and then there's this kind of marching through. It's not quite as elegant as this picture makes it out to look to be, but this is some evidence that maybe in the inner galaxy of the Milky Way, you have this kind of shock picture of what's going on, which is some kind of argument for some kind of standing wave picture. Maybe it's not exactly the two-arm spiral shock model, but it's a nice argument, and which is why people who think about the Milky Way a lot like this picture in some ways, because it does reproduce some things. But there's more than one way to make a spiral. And I like to make this analogy between like a stream and a spiral. And when I say a stream here, I mean like literally a stream that you find outdoors. So you might say, I see a stream outside, and therefore it must have rained. And that's certainly possible. But a stream is a natural way for water to get downhill. And so if there were a spring, for instance, the spring could also create a stream, right? And so we shouldn't be surprised that there are some streams that come from springs and some streams that come from rain. And similarly, spiral arms are energetically just a favorable thing to do in a galaxy, right? They really nicely transport angular momentum, keep the angular momentum, but you reduce the energy of the system, and so it's totally reasonable to have more than one explanation for a spiral arm. So here's what you see in simulations. This is the fire collaboration simulation, and you see all this spiral structure. None of it sticks around for a long time. All of it gets sheared apart. Any one snapshot, you can see spirally things, but there's no real sense of a standing shock that sits around for many rotation times. And so modern people who are working on simulations often look at this two-arm spiral shock model and say, what are you talking about? That's not how any of this works. Really, you're seeing this accretion onto the outside, it's shearing apart, and you see these local instabilities that generate spiral-like structure, but there's nothing like these standing situations. I like this piece of the same movie because it flies you right into the problem that is my entire life, which is that we live inside the Milky Way. Okay, so it would be very great to look at the Milky Way from the outside and understand what's going on, but instead you have all these really up-close particles, which look horrible and terrible. But the Milky Way is a really important place to study this, because if we think spiral arms are where stars form, sort of definitionally, if we have different mechanisms for forming the spiral arms, we'd like to know whether the star formation regions we're looking at are caused by shocks or are caused by these transient spiral arms, because that's going to tell us something about how star formation works. So yes, we can go look at external galaxies and we can learn things about spiral structure. That's great. But those star formation regions we cannot study in the kind of detail we can study in the Milky Way. So especially with things like Gaia, it's really nice to understand what is going on in these spiral arms. OK, so how do we study the spiral arms of the Milky Way? Well, we use diagrams like this. So here is the sun again at the left. Hope every picture from now on is the sun at the left, the galactic center in the middle. And these are different lines of sight. And along these lines of sight at various different galactic longitudes, you see different velocities. So this is the inner galaxy, the part of the galaxy inside the solar circle. The rest of this is the outer galaxy. And you can see as you go through the inner galaxy, you have this annoying problem. It's called the distance ambiguity, where something at different velocities, so the colors here are radial velocities, so this is plus 10, plus 20, plus 30, plus 40, plus 50 kilometers per second. Something, parcel of gas you see at, say, plus 20 kilometers per second could be here, could be there. In the outer galaxy, it's not as bad. You don't have a distance ambiguity. And so, if you have a flat rotation curve, so you know that all of the gas is rotating on cylinders at 220 kilometers per second, like we were all taught, and is the word of God, then you can very easily infer from a given distance, a given velocity, you get a specific distance. So this is the sort of standard diagram we use to try to make sense of what's going on, because we cannot get distances in the Milky Way very well, Gaia notwithstanding. But for gas, it's very difficult. But what we can do is measure velocities. We have lots of information from radio surveys about the velocities of these parcels, and from that we can try to reconstruct what's going on in the disk. Okay. So this is what happens when you try to do that thing. So I was talking about these velocity fields. When I'm showing you here, and I'll show diagrams like this a lot, so it's worth your time to understand what the heck I'm talking about. The x-axis here is galactic longitude, and the y-axis here is VLSR, the local center of rest velocity. The gray here is the 21 centimeter, and the, what do we call this, Viridis, is the CO gas. Okay, and I'm drawing your eye, so you see all these features. And when galactic astronomers, galactic interstellar medium astronomers talk to each other, they talk in this space, this galactic longitude velocity space. And you see all these features, and some of them are incredibly beautiful and clear. And what I'm tracing out for you here is what's called the Perseus arm, which is an arm in the outer.
You're a true galactic astronomer because you plot it backwards.
Of course. Of course they plot it backwards. Like you would see it on the sky with your radio eyes that you obviously have. Yes, I do plot it backwards. So this is, the little red dots are masers, and masers are great because we know both their radial velocity and their proper motion and their three-space position, and they're tracers of star formation. So they're really good for understanding spiral arms, and I'll come back to them. And you see these little tracers, and you have this very nice long continuous arm that follows this beautiful trace of CO gas and H1 gas in this space. And so people have long used the Perseus arm because it's so clear. It's in the outer galaxy where you don't have, it's largely the outer galaxy, this is the outer galaxy here, where you don't have this distance ambiguity, where things are folded on top of each other. So it's really beautiful, and it makes a great test bed for spiral theory. So again, I'm going to rotate this diagram. There we go. There's the sun, there's the galactic center, here's the Perseus arm, these little dots are all the masers, and this is somebody's possibly fanciful diagram of where all the star formation, where the star forming spiral arms are. And you see they're connecting up these different regions of masers. Okay, right, so these are the high mass star formation regions, these masers. Okay, so enough of introduction.
Sorry.
Please.
To go back to the introduction. If you go one slide back, so in what direction relative to the sun does the Perseus arm move? You go one build forwards on your slide. So it goes away from the sun?
It goes away from the sun, yes.
Like how does the Perseus arm move compared to the sun?
Yes, it has negative velocity. It's moving towards the sun. Or the sun's velocity is faster than it. It's moving differentially. The sun is moving differentially past it. So everything is rotating like so.
At some stage, we'll run into the Perseus arm.
Well, it depends on if you think it's a standing wave that sits there.
Oh yeah. Okay.
Which we'll get to in a second. And by second, I mean 40 minutes. Okay, so here's what I'm going to try to convince you of during this talk. Kinetic tomography is a thing, and also interesting. We can reliably map interstellar medium flows across the near side of the Milky Way. The velocity field of the outer galaxy, where the Perseus arm lives, is inconsistent with spiral density wave theory. And the Perseus LV feature is in part an illusion. Okay, we'll see if I successfully convince you of these things. Not entirely certain. Okay, so kinetic tomography is interesting. So tomography, classical tomography, medical tomography is you slice something up, you have slices of things, and you reconstruct something in 3 dimensions. That's the sort of classical medical tomography, and as evidenced by this little movie, it's gross. Now, stellar tomography, which I won't be talking about much, is going from a 0D piece of information to try to reconstruct some kind of 3D. So if you were with us during the Gaia sprint, you sat in the hidden planetarium and experienced flying through a maelstrom of stars. And so you could try to reconstruct some stream or something from these 0D points. Okay. So the gas tomography I'm going to be talking about takes points in space. Here, these little blue dots are stars. There's the sun, that's 100 parsecs. And tries to reconstruct the 3-dimensional structure of space by some kind of dimming of these stars. Either it's an absorption line, sodium-1, which I was just talking about earlier today, or you can do this in dust. Okay? And back in the way back days of 2011, I looked at these diagrams that were the state of the art at the time, and I thought, this is really cool. We have a 3-dimensional picture of the interstellar medium. What cool stuff can we do with that? Well, it's gotten a lot cooler. And I just want to make the argument to you that we live in this era of just incredible tomography machines. I'm listing a bunch of things here, 2 spectroscopic, 1 with parallax, and 2 photometric. I'll talk a bunch about pan-stars and how they're able to reconstruct the three-dimensional distribution of the ISM using pan-stars. But Apogee and SDSS-5 have this spectroscopic capability that allows you both have precise spectroscopic distances, but also measure some absorption lines. And these two things together are really powerful for doing tomographic work. And Gaia as well. Adding this together is going to be amazing, and of course LSST on the horizon is going to provide an incredible number of stars across a lot of different photometric bands. So it is time for tomography. So I'll just briefly speak about Greg Green, Eddie Schlafly, Doug Finkbeiner, and co.'s work on the topic. But roughly speaking, if you have some prior as to where you think a star sits in a color space, really a magnitude space, you can say, well, I have some observation, and that's either this star this much reddened, or this star this much reddened. We know that dust reddens starlight, so you can make some kind of guess as to how far away the star is and how reddened it is simultaneously. Now that's not enough, but if you have a lot of stars, you can put them all together. So any one of these stars gives you some probability distribution function in some kind of distance modulus reddening space, and so you say, well, this star means that the interstellar medium meets these criteria, or one of these criteria. But if you have, say, a small 5 arc minute or 6 arc minute pixel, you might have 1,000 stars, you multiply them all together, you make some assertion that the reddening has to increase as you get further away, and you can fit this with some kind of model. Okay, so that's to sum up a talk that Eddie or Greg would give over the course of an hour and a half. I'm just telling you the basic idea of how you build a 3D map out of a bunch of stars where you only have photometry and no distance. Okay? Your main sequence fitting, roughly speaking, but like the cool kids do. And it's incredibly pretty. Okay, so this is this beautiful movie, you're moving around, you see all of these molecular clouds that are gorgeous. But if you talk to my collaborator, Carl Gordon, the first thing he said to me was, so what?
Wait, I just want to understand your pretty movie.
Okay.
This is a map of the ISM. Yes. Created based on constraints on stellar reddening of stars.
Absolutely correct.
Okay.
But what Carl says about this is, so what? So you have a 3D map of the ISM. So now I know how far away some molecular clouds are. That I'm sure is helpful for some of these models. But what does it tell me about the interstellar medium? And by itself, I think it doesn't tell you that much yet. But what I'm going to argue is this DV diagram is the killer app for studying formation, right? Star formation, galaxy formation. This is what we are interested in studying. We want to get at the velocity field of this material. So you have, from a radio survey, where you have the 21 centimeter line or the CO line, you don't know anything about how far away the material is. From a reddening survey, you don't know anything about its radial velocity. But if you can somehow put them together, you can learn more. And in fact, in this case, where the far piece is moving towards you and the near piece is moving away, you have convergence. Whereas in this piece, you have the far piece moving away and the near piece moving towards, and you have divergence. Right? This is explosion, this is formation, right? And yet they would look exactly the same in these things separated. Right? The projection of this in this dimension or in this dimension is this or that, but if you put them together, you can actually get at the physics of what's going on along the line of sight and study this process of formation. So I'm just arguing that this is how we solve the continuity equation, at least along the line of sight. Transverse stuff I can't do yet, sorry. Okay, so hopefully I've convinced you that kinetic tomography, that process I'm discussing, of figuring out the velocity field of the material in the interstellar medium is a thing worth doing. So now the question is, can we do it? So here's what Kirill Chernyshov and I set off to do, these many years ago. We took the three-dimensional dust map. This is the state it was at the time when we got started. And we added to it a 21 centimeter map, which is where my expertise is, and a CO map, okay, so carbon monoxide map. And we made a bunch of very, very bad assumptions, including the idea that you can just multiply for any parcel of gas, the amount of CO and the amount of H1 times some cofactors should get you the total amount of reddening, which anyone who studies the interstellar medium will tell you is a terrible, terrible assumption. There's XCO factors, there's all sorts of bad reasons, which I'll explain shortly. But let's make some bad assumptions to get started. So basically, here's what we do. So how do we do this? How do we connect these pieces together? Basically, for each parcel along the line of sight, so like this little blob, we guess that its velocity is its flat rotation curve velocity. We have a distance, We should be able to, knowing the flat rotation curve, know what we should expect. And then we try to, and so we lay that down on some grid. Then we let the velocity vary. So we let this parcel of gas, move up and down to try to match this little blob here, okay? And then we add some regularization cost so that we don't allow for sharp jumps across the sky. So that's the procedure I'm going to show you. I just want to give you a preview of what we're doing. It's not that complicated in the end, but okay. So let's just start with the dust map. This is a dust map. We've totally gotten rid of the B dimension. It's just L around the galaxy and distance. In fact, let's just focus on this one little spike, and I'm going to show you a little histogram of it. So this is just a histogram of how much dust there is as a function of distance towards this particular direction. Straightforward. Now I'm going to say, well, along this exact same line of sight, I also know something about how much gas there is as a function of velocity. That's this axis. What I'm trying to do is relate them. Okay? So the first thing you can do is say, let's assume a perfectly flat rotation curve. So this color yellow here is showing how much each parcel deviates from what you expect from a flat rotation curve. So at any particular place in the galaxy, there's a rotation curve. By just geometry, it gives you some radial velocity, and this is just deviation from that. And so right now I'm saying 0 deviation. So you take every one of these parcels, you push it here, and it goes down here. You take this one, it goes over here, right? And you build this thing up, and lo and behold, it totally fails. Okay? A flat rotation curve is terrible at reproducing what is going on in terms of the radial velocity. So now you can do something fancier. You can use the Clemens rotation curve from 1985, and it also totally fails. It fails less failingly, but it does fail. Then you can say, well, shoot, let's just let all these little parcels move back and forth as much as they want. Maybe we'll not let them go past red or past blue, but they can move as they like, and you get something that works great. Now, of course, you have like a huge number of free parameters, and so of course it works great. If you can't fit this, you got problems. But it does work great. But one thing, extra cost we can add to simplify the problem is we can say, look, here it's saying that a cloud that is, 1 pixel away, 5 arc minutes away from this one is a totally different radial velocity. That doesn't sound physically reasonable. So let's add some kind of regularization cost. We're just basically, we call these Markov springs, but they're essentially just a regularization cost where we say we're going to add an extra cost to our model for it to be not smooth. So here are the Markov springs on the sky, and it makes sense, right? You've got a cloud. Yes, there are going to be some boundaries where there's a blue cloud next to a red cloud. There's some kind of turbulence, but on small scales, we know that the turbulent cascade, dies, so it all kind of makes sense. So you go from this to this, and your fit is, of course, worse. It has to be worse. If it's not worse, you're doing something wrong, and you get some kind of thing out. Cool. Does it work? So one way we can test whether it works is we can test this against the high mass star formation regions. These are the masers. The masers are great because A, they trace star formation, which we're interested in. B, we have their positions in 3 space from parallax, because we've got them from VLBI. And C, we have their proper motions too, so that's extra bonus. Great, so we can compare them, and boom, it works. So what you're seeing is the top-down map. This is our result. We're only showing you the average across the disk, because we actually have the full 3-dimensional information. And this is the radial velocity residual, so what you would see beyond a flat rotation curve. So you see blue areas and you see red areas, and each one of these is a maser. And the inside is the maser velocity, and the outside is we get at the 3-dimensional position of that maser. And you can see, you can barely tell the color difference. There are places where we fail. There's a failure. But this thing has basically a reduced chi-square of like 1.3 or something. We do great. So that's great. We are recovering the 3-dimensional velocity field of the Milky Way, and this is the Perseus arm. But there's a problem. There's a lot of problems. One problem is we're only testing this map at these high mass star formation regions. And the whole point is we're interested not just at where the stars form, but at the flows onto the stars, right? That's what I was saying. We're trying to do this surface integral to understand the convergence or divergence at the spiral arm. We're not just interested in the high mass star formation regions themselves. Second, for those of you paying attention to this particular aspect, AV is not the same as CO times something plus H1 times something, right? There exists dark gas, and that's this lump here. Okay, so this is AV on the y-axis for the Aquilo-Fucus region. This is CO plus H1, some kind of guess is the total protons, and it goes fine in these low extinction regions, but as you get towards an AV of about 2, everything goes totally to hell. Okay, so maybe this works, but if it does, it's just because we're lucky. And then 3, I think this is probably one of the worst parts, is that the radio distance is to infinity, right? We see everything across the whole disk. Especially when you're looking towards the center of the galaxy, all of these velocities get conflated in some horrible way, whereas the stars all run out when either they're too far away and too faint, or there's dust in the way. So all of these create big problems. So Kirill had the very good idea to start talking to Gail Sosowski, who happened to be across the street at the time, and start getting interested in apogee. So I probably don't need to tell this group too much about apogee, but roughly speaking, it is this very high resolution spectrograph in the infrared of lots and lots of red giants across the galactic plane. There's lots of other stuff apogee does too. I'm not going to get into the details, but from my perspective, this is what it provides. And what's great about apogee is that it has this amazing diffuse interstellar band that Gail popularized. And what she showed is that this diffuse interstellar band, first of all, gives you velocity. That should be obvious. It's a band. It's a little bit wide, unfortunately, so getting precise velocities is hard, but it's very nice. But critically, it is totally linear with AV. So equivalent width of the dib is linear with AV. There's no dark gas component like we had in the other plot, so that's great. And then third, there's just beautiful distances to these things. So these beautiful spectrophotometric distances, they're better than Gaia by the time you get out to a kiloparsec or so. So it's a great tool for doing the same method, or sorry, for studying the same problem. So you can take all of these stars with these diffuse interstellar band absorption lines, and you can try to differentially measure them and figure out what the velocity field of the Milky Way is. The magic, let's see, actually, I have, I'm trying to remember what my next slide is. The magic of this is that Kirill was able to, by using a hierarchical Bayesian method, reconstruct the velocity field without having to first reconstruct the density field. And that's a critical part of this. This is such a sparse sample. There's only 150,000 of these stars, which for us is quite sparse. The interstellar medium has lots of small-scale structure, and so you need to somehow reconstruct the velocity field without intermediately making a density field map. And that was the big revelation that let him do this. So now we have 2 maps. This is the same map I showed you before, but at lower resolution, dumbed down, the gas and dust kinetic tomography, and the dim kinetic tomography. And they have noise, and they're not identical, but you're basically seeing the same qualitative results across these 2 maps from 2 methods that have no overlapping code, except for like AstroPy, and have no overlapping data at all, okay? So Kirill was very forceful that he really wanted to do this 2 ways because we were not sure we were right. I was sure that he was right, but he wasn't sure that he was right. And indeed, he was right, at least at the level that these 2 maps are similar. Okay, cool. So now what we want to do, slight aside, a cool thing you can do, and that we're doing right now, is do the same thing but through an individual molecular cloud. So we now have data from apogee going straight through a single molecular cloud, where we can actually measure the velocity field of the material accreting onto the molecular cloud. We believe, and I have not reduced the data yet, we believe we can actually measure the free fall accretion onto this molecular cloud. We'll see if it works, but if it does, it'll be really cool because we'll actually get to see a molecular cloud forming live, I think, for the first time. Okay, cool. So,
why is it called the California Project?
Because it's on the California Nebula.
Oh, I didn't know there was one.
Yeah. And also, just to point this out, this is the coverage of apogee that we used to make this map. This is what we're going to get for SDSS5. So this is going to be amazing, but zone G. Okay, great. So I'm going to argue that this velocity field of the outer galaxy is inconsistent with spiral wave density theory. Okay, great, we made a map. So what? Well, this is what. So there are spiral density wave models that reproduce some of the features of the Milky Way. So I'm showing you 2 here. Lots of people have done these. Kirill worked with these authors and got all of their data from snapshots. So these models have these forced spiral potentials. That's why they look so beautiful. And they don't have live disks. And they can match up all of the detailed substructure, the far 3 kiloparsec arm, et cetera, the Perseus arm, the outer arm, et cetera, that people believe they're seeing in these maps.
So, are these bar-driven spirals?
I think there is a bar in this spiral, but the spirals aren't being driven by anything. They are forced.
Oh, they're put in.
They're just put in.
So they all have their own pattern speed, or they're all coupled somehow?
A forced pattern speed, yeah.
For the entire system?
For the entire system, I believe. It could be that this is separate. I would have to go back to the literature to check. I'm not certain. So they reproduce both what you think you're seeing in sun's upside down, what you're seeing in the local arm, and the Perseus arm, and the outer arm, and the interskin, blah blah blah, and also this LV diagram. Okay, but we also looked at these live disks. So the live disks aren't trying to predict things in gory detail. This arm is this arm, this arm is this arm. That would be very hard. But they have live potentials. So you're not forcing the spiral arms in a particular way. And these spiral arms are what are called material arms. In general, what they find in these simulations is it's hard to have a very long-lasting spiral arm that sits around for many rotation periods. These things appear and they disappear. They accrete and they dissipate. So they're often called material arms. They tend to have this much sharper pitch angle. You don't see this very, very tight winding as much. Yeah, I don't know why they didn't provide me that little diagram.
But these, these look like, what I think of as these sort of flocculent spirals that are short-lived. When you have a disk that's unstable, lots and lots of noise.
Sure.
But we live in a barred galaxy.
Sure.
And barred galaxies tend to, out to the outer Lindblad resonance, Perseus may be beyond that. Long-lived spiral features. So I'm just not sure whether these are the right theoretical models.
Let's find out. So what we can do is take this velocity field, and we can compare it to the velocity field we see in these models. So I'm going to do that. Boink. So what we've done is we have not done the details of exact simulated observations and all the rest, because it turns out that the very bulk features are quite obvious. So we can compare all these different simulations to what we see in the observations and see what we see. So the first point is that some of these are just slow. They just don't produce much in the way of radial velocity fields at all. Everything is just kind of a taupe color or something here. You don't see these strong plus or minus 30 kilometers per second features towards the outer galaxy. It all just kind of dies away. Okay, that seems quite inconsistent with what we see in the real data, where we see these huge, many kiloparsec long, very strong features. Okay. Many of them seem to drive radial flows. So if you look here, you see a positive radial velocity on this side and a positive radial velocity on this side, or a negative on this side and a negative on this side. Whereas here we see an asymmetry. So this asymmetry is most likely coming from some kind of azimuthal component, right? It's an accelerant. It's the disk is speeding up or slowing down, and so it looks blue shifted on this side and red shifted on that side. Here you're seeing a radial component, and of course in the simulation you can just go check, and indeed these are radial flows. So you see these radial flows into and out of the spiral arms, and that is a fundamental thing that you expect from many of these models. But one of our models reproduces a lot of what we see qualitatively. And in particular, it reproduces divergence at the spiral arm. Okay? So if you look at these classical models, right, I showed you that early diagram where you have a spiral arm and there's a shock that goes in and it turns. Okay? That means you have an inflow into the inside of the spiral arm and it's moving along the spiral arm afterwards. Okay, that means you should be seeing an inflow into the inside of the spiral arm. And we simply don't see that. In fact, what we see here is that we see it is blue shifted, more blue shifted on the near side and less blue shifted on the outside of this particular spiral arm. Meaning to say, the place where we have the best data, we're seeing much more consistency with this picture where we have a flocculent type spiral picture. So these data are consistent with the idea of a disrupting Perseus arm. So here again, near side a little bit blue shifted, outside either not blue shifted or partially blue shifted, but as you see, this is a divergence here along the line of sight. And that's actually what we see in the stars as well. This is Baba et al. 2018, and you can see, and this has been seen now in a couple of different studies from Gaia, that the stuff on the near side is coming towards, and the stuff on the far side is either static or moving away. Okay, so we see this divergence in the not super young, but relatively young stars, just like we see it in the gas. That's really, really inconsistent with the classical pictures of spiral models. Okay, so how does this all hang together? I'm going to try to make an argument for how I think this whole picture works, and how the Perseus LV feature is in part an illusion. And this is the moment where you say, how much time do I have? 4:11. I don't even know.
10 minutes.
Okay, 10 minutes, that sounds great. Perseus LV feature is part of an illusion. So the pitch angle that we find in the outer galaxy, or anywhere really, is dependent on maser arm identification. So let me show you what I mean. You're gonna have to watch the colors a little carefully here. So here's a simulation, and here are the masers. So the pink ones are the Perseus arm, and I want you to just keep your eyes on this little patch and this little patch here, okay? So what you're seeing is that these are all connected up together. But we can use a different simulation, and it looks just fine like this too. But I've changed the color, okay? I've changed the color of this guy. And these are no longer the same color as those. Okay, so I'm just going to go back. So again, watch these. Boop. Okay, so what's going on is we are using the LV diagram to guide the eye. Any one of these little blobs, if you imagine taking away all the colors and taking away the background, you're just going to see a bunch of points. Nobody sees a long, continuous, beautiful spiral arm with these. And so when Adrian Price Whalen was like, there aren't spiral arms, why do people keep coloring these spiral arms this way? I was like, my child. The way this works is that you have to use the LV diagram. The LV diagram is what really connects these things together. And by eye, it is quite obvious that this stuff connects delightfully right into this stuff. And the way I paint them here is wrong. Watch this space. So if you have the flat rotation curve, you can turn this into this. Okay? That's how we make our spiral arms. This is work by Ku, my former office mate, Evan Levine, made really nice maps like this. This is work by Marc-Antoine Michel Dechaine, where he took apart all of the DMCO map into lots of little blobs and made nice velocity fields from these things and got some distances, which is great. But it requires the flat rotation curve. And what I just told you is the flat rotation curve is a lie. There is no flat rotation curve. There's large bulk flows. They are not trivial. You cannot ignore them if you're trying to understand how this picture is made. So let me show you in detail. So here's one sight line with lots of masers. Everything should work just great. This is what you get from a flat rotation curve. You see it totally misses the masers. Okay, what's going on? Well, we're going to correct the rotation curve. Maybe they're speeding up, they're slowing down. Don't worry about it. Nothing to see here. This is what most people think is going on. This is what kinetic tomography sees. See something totally different. We see this very big difference in velocity from what you expect. And the point I'm trying to make here is this very large range of distances corresponds to a very narrow range of velocities. So this is effectively a velocity caustic. We're bunching up a huge part of one parameter space, and we're pushing it into another piece of parameter space. So it looks like there's a lot of stuff all bunched up at the same velocity, but really it's over a very large range of distances. As Jerry Ostraker taught me, most things that are cool were done in the 70s first. And this is a great paper by Butler Burton, which I refer to as Butler's curse, or Burton's curse, which Butler loves, turns out. His point was that if you have a completely smooth disk and you inject a velocity field, a reasonable velocity field, you can generate this LV structure. So again, this is radial velocity, this is galactic longitude, and you've got all this crazy structure in here that looks like spiral arms, but it's from a disk that's completely smooth. Now, of course, that's unreasonable. You can't have a perfectly smooth disk. But his point was that a reasonable velocity field generates structure. And this turns out to have caused some huge rift in the field, and people still hate each other, and I don't know the details. But so I want to show you what that looks like with what we actually now know from kinetic tomography. He was making some assumption. He was saying, let's say that the velocity field looks like this. You get all this structure. Well, let's look. This is what you get if you just take, get away the punchline. If you just take all the nearby stuff where we think we believe our kinetic tomography work, this is what you get. You get a perfectly smooth distribution. You get some bunching up just due to the projection effects. Now let's look with kinetic tomography. Wham. So perfectly smooth disk using the velocity field we have gives you the Perseus arm. Now, I am not here to tell you that these masers are wrong. I'm not here to tell you that these molecular clouds are not a thing. They are obviously a thing. These masers aren't the right distance. But connecting from here all the way to here to get to the next set of masers, I'm skeptical of because of this velocity field. Okay? And again, this is the key to making a nice long spiral arm that has a shallow pitch angle, connects everything up, and gives you this beautiful classical picture of spiral theory, which everybody who works on the galaxy thinks is real. So let's go into detail. The ISM isn't smooth, okay? The assumption the ISM is smooth is always a bad assumption. Let's go look at all these molecular clouds that connect this maser region to this maser region. There's this bridge here. That's what guides the eye. That's what makes this all one big piece. These are molecular clouds that come from work by Marc-Antoine, where he took the whole survey apart into little tiny pieces. So you can look at any one molecular cloud. You can look at what the dust looks like along the line of sight to this molecular cloud. First of all, you can look at the CO, and indeed it has this big nice spike, exactly where you expect it. You can look at the CO off, and you see less. If you look at the difference between these in dust, you indeed see there's a bunch of nearby dust, and then pow, there's this nice big spike right at 2 kiloparsecs. Bob's your uncle, everything works. This molecular cloud is at 2 kiloparsecs. We see the reddening towards it, and no reddening around it at 2 kiloparsecs. So that means that this cloud, as traced by the CO, is creating dust at this distance. Great. Sometimes, though, sometimes it works, but sometimes It doesn't. And you get, everything works great. This cloud, you look around it, you see this nice big spike in CO, and wham, it's off by an entire kiloparsec. So this cloud, which is at a velocity consistent with the Perseus arm, is at 1 kiloparsec for some reason. And then sometimes the method totally fails, and I throw those out. Yeah, the interstellar medium is complicated, sorry. So this is what the plot looks like. So I've taken these clouds and I've color-coded them by their distance. The gray ones are ones where I can't measure the distance, and the ones with color are distances ranging from 1 to 5 kiloparsecs. And you see it's just a mess. These things should all be sitting at about 2 kiloparsecs, and there's one that's at 2, there's one that's at 2, it's a mess. And if you look at it in the 3 space, this is what you see. This is the sun, this is the Perseus arm. These are the masers. There's other masers down here off the map, and it's just a mess. There is no connection between these things. There is no arm here. There's an little armlet here, and there's stuff over here, but this is just a giant pile of molecular clouds like you might expect. You might not believe my distances, but man, it's that nice, and it's that nice, and it's that nice. These little blobs all totally independently measured. So what I'm showing you here is that this idea of a long, contiguous, shallow pitch angle Perseus arm may itself just be a velocity space artifact. You can't connect all these things together because you're making this assumption of a flat rotation curve, which is just not how the universe works as far as we can tell. So this could be a problem for the entire star-forming disk, right? I've given you this whole long spiel about this one little piddly arm. I think it's a very nice arm. It's in a nice part of the galaxy. It's very useful to study. But the problem is that this region where we've been studying has a relatively, medium steep relationship between its radial velocity and its distance, okay? And so anything shallower than that means that if you have bulk velocity fields that can mess that up, then any kind of mechanism where you're trying to infer distance from velocity is broken. And so anything outside these red areas, there's the sun, there's the galactic center, anything outside these red areas is an area where we could be having a significant problem with measuring distances in an accurate way and measuring the structure of these spiral arms. So I'm just trying to point out that this isn't just a problem for this one particular case. In general, if you're trying to use the LV diagram to infer the existence of spiral arms, you may well just be inferring the existence of velocity fields, velocity caustics in the disk, which are almost certainly prevalent everywhere.
You've violated your rule on where the sun is.
Yes, I'm really sorry about that. If you'd like, I'll go over
Okay,
it.
it's okay.
Okay. But yes, that's the sun, that's the galactic center.
That makes much more sense.
Yes. Yeah, I'm really the worst. But I'm just teaching you how to read the literature. It's all a total disaster. There's no consistency at all. Okay, so conclusions. Kinetic tomography is interesting. Also a thing that has a name. We can reliably map interstellar medium flows across the near side of the Milky Way disk. I showed you 2 different methods using 2 different data sets that pretty much gave you the same answer, more or less. The velocity field of the outer galaxy is inconsistent with spiral density wave theory. I'm arguing that spiral density wave theory makes quite specific predictions about the velocity field, and we have yet to find any kind of simulation, or for that matter, analytic model, that gives you anything that looks like what we see in the velocity field of the outer galaxy, especially in the sense of this diverging arm. You don't have diverging arms, the arms that live forever. And finally, this LV feature in the Perseus arm that is really what people appeal to when they talk about really long features is, I think, in large part an illusion. And we should really be thinking about these individual pieces where we see star-forming regions and thinking about them as little flocculent armlets. And I'm going to leave it there. Thank you.
So this is really interesting. I mean, I remember an old argument by Kontopoulos that with spiral density wave theory, you basically can't extend a spiral wave beyond the ultraharmonic 4-to-1 resonance, because there you get basically a phase shift in the ellipticity of the orbits that you stack together. So if you look at the Perseus arm, you assume that basically the Perseus arm most likely would follow the pattern and speed of the bar. At what radius would the ultraharmonic fall, and do you know where the Perseus arm is?
I think it's further. I think it's further out, because the long bar, the tip of the bar is what, 2 kiloparsecs out? And the Perseus arm is only like 10 kiloparsecs from galactic center.
So how far is the outer limb of resonance?
Don't off the top of my head. I'm not sure if we know. I'm not sure if it's agreed upon in the literature. But David probably has thoughts.
People put it as close with the OLR as here.
Right.
But there's debate on what the OLR
I love your DIB, use of DIBs. Like, I mean, you know, like when some stuff in my PhD was a very obscure field, and I guess now there's lots of work going on, and really, really cool. So I'm wondering, are you then saying, like, you know, that if we were to look at the galaxy from the outside, we would have had broken arms, like we would sort of have things?
I'm not going to make too much of an argument about the stuff that's close to the bar. I think the bar does induce, like the Scutum Centaurus arm, which some people might call the molecular ring, if you're familiar with that terminology, is very clearly a very strong spiral arm. And I would not at all argue, we don't have data yet to argue that it's not a long-lasting feature with, you know, a velocity field consistent with a more classical mode, like a two-arm spiral shock kind of mode. But in the outer galaxy, yeah, I think we do see a much more flocculent picture, or at least a picture that's inconsistent with a classical, you know, long-lived spiral arm.
So, I mean, then I look at a picture of the Roman galaxy, and I don't see this. Do we see this in other galaxies?
That's a good question. I was thinking, like, what if I were to make an argument that, yes, we see a transition from something shock-like on the inside, something long-lasting on the inside, to something less long-lasting on the outside. Do you have an example? And no, I haven't thought of one, but it'd be interesting to check and to look for. But it does seem to me that when you're very far from a bar, or you have a very weak bar, the only examples we have where we really believe this two-arm spiral shocks when you have an external perturber, like an M51 or like an M81. That's where it's really clear. I don't know if we have lots of great examples otherwise.
So there has to be a perturber in order to get spiral arms? Is that what you just said?
To get these beautiful two-arm spiral shocks that have this very classical picture. If you have an external perturber, you do seem to see something consistent with that.
So that was my question. My question is to you, is what an Astro 100 student comes to you and says, or you're in front of a lecture hall of 100 students and you're supposed to tell them why galaxies have spiral arms. What do you say?
Well, I think it's because they're energetically favorable, roughly speaking. I think for the Astro 100 level, which from a dynamicist perspective.
So the same reason that stars are round, galaxies
Yes.
have spiral arms.
That from my perspective, and I feel like I'm kind of at from a dynamics perspective at an Astro 100 level, maybe 200 level, but I would say that that's the most fundamental idea, is that they're a very energetically favorable thing to do, and so we shouldn't be too surprised that there's lots of different ways to make them. I think dynamicists would say there's a lot of details in there, and I would agree with them.
Do you think it's possible some accretion event just messed things up in that area? Something like that? Have you looked at that at all?
So it's one question that Kirill and I have been asking ourselves as the Gaia literature has gotten richer and richer at an incredible pace, is how consistent is this velocity field with old stars, right? Because if this is being created by some kind of shock, it should be very different than the old stars. And if it's being created by if it's being created by something dynamical, then that dynamical thing is going to affect them both kind of equally. And we've seen mixed results on that, just looking at what's coming out. So I think time will tell if there's a significant difference. But there are a lot of places where we're seeing consistency with the stars, which would not be inconsistent with the picture that you're putting forward. That being said, I just showed plenty of models that did a pretty good job giving you similar velocity features, similar levels of divergence, all these things in the outer galaxy, which just kind of works. So I can't really say.
Have you looked at the galactic anticenter and the velocity field there?
Yes.
So what I remember about that region is that if we had nice flat rotation curves, axisymmetric galaxy, in the anticenter region, the centroid of the H1 distribution should be at velocity 0. It's not. It's like 15 kilometers a second off.
Yeah. So actually, what I would say is that if you look at like figure 8 or whatever it is from the 1972 paper, what you see is toward the anticenter there has to be a radial velocity into the inside of the arm, right? That's a very, very generic prediction from two-arm spiral shock theory, and in general a prediction from these theories that there should be a flow into the arm, which is to say there should be a positive redshift. It is just not there. So we don't see that. So in our data, what we see, in fact, I can just go back to it, it's here somewhere. You don't see too much in the way of a redshift towards the anticenter. Come on, you turkey. Yeah, so you see that this is all just kind of yellowish. Maybe there's a little tiny bit of a shift. Certainly not 15 kilometers per second. But you can, you can just see this in the H1 data itself, or the CO data itself.
But if you go back to the H1 data,
It's a long way.
maybe the previous plot, so the classic LV.
Oh yeah, classic LV diagram plot. Let's see. Did I miss it? I think I missed it.
You have one.
Yeah. Hold on.
Yeah, so if you look at the central data, at the end, there, the centroid of the H1 distribution is not at 0.
Disagree?
Unless the H1, if you
We
look,
can stick.
Yeah.
yeah, if you.
That's my PowerPoint. I'll just tell you what Roberts predicts is like this. It's like the centroid should be here. It's not. I mean, there may be an offset here of a few kilometers per second. I can't.
Yeah, that's about 15.
Well, I have the highest resolution. I made the highest resolution H1 maps of that region, so we can go look at them.
Yeah, no, I'm surprised that I mean, that's at least, where it looked in the 1980s. Right?
It's changed over time. Yeah, I'm not certain.
I haven't, I haven't looked at it since, but I remember that it was one of the things that convinced me there had to be asymmetries in the outer galaxy. Was
Yeah.
There's funny things going on there, and I haven't gone back and looked since.
Yeah. No, I think we don't see that, and that was one of the things that it's funny because I had the exact completely opposite thing, which is that I didn't see that, and yet it was quite clearly predicted from the original work on the topic, and it does seem to be quite consistent prediction of any kind of long-standing arm is that there has to be a flow into it, and then a flow along it, and if there's a flow into it, then it has to be redshifted, and it's not there.
Great.
Can you go back to the comparison of the two methods of the velocity flows? Or at least, okay, that's fine. Get them down a minute.
That.
Perfect. So I have a couple of questions about this. So one is that, well, let me start off with the complaint first of all. So you said they're consistent, but if I look up at say 2 kiloparsecs up at plus 20, 15 kilometers per second, they're actually very different, right?
Where? Here?
Down a little bit, to the right a little bit, yeah, somewhere around there, right? I mean, they show the same, like, you see this red
This and
line
this?
is going, it's much steeper on the left plot than in the right plot, right?
Hard, tough crowd.
I know.
Well, okay, but I guess you're saying they're consistent, and yet, I mean, if I were to just difference the two, in that area I would get large differences.
Yeah, so we have a large amount of the paper talks about this in detail. The question is how much of this is errors in this map, and how much can you attribute to that? So yes, we need more data, is what I'm supposed to say at this moment. But yeah, I would love for these to be more consistent than they are, and I think there are differences.
That's where the point of like comparison with the models, you really just care about like the radial, if you're moving towards blue shifted or red shifted.
Yeah, so it's at the level we're comparing with the models, I think it's quite clear that these are both consistent with, more or less consistent with one of the models and inconsistent with all the rest.
So my second question, actually my real question, which is what are the scales? So this is probably answered in the paper, but what are the limit on the sort of smoothing scales here? Like how could there be velocity flows which are significant on smaller scales that you're effectively smoothing over here?
Yes, so let's go back to this picture. So we know those exist from this map. So this map has a resolution on the sky of 5 arc minutes. Right? We paint every pixel in the green maps with a radial velocity. And we know there are problems in these maps. There's all sorts of weird things that happen. But we also know, I mean, I'll just show you an example. Like this is saying that our prediction at this point is this orange color, and that it's consistent with the maser. But that maser is embedded in kind of a blue region. And we're just, I can't remember if this is an aperture slice.
Too large.
Yeah, so there's lots of substructure where we do see velocity fields that change. I think one of the next things we want to do, now that we've shown that these two methods are consistent at a level where we can compare the simulation, we'd like us to combine the data. So I think a next project would be to take this data and now the DCAPS data, which fills in all of this, and the Apogee 2 data, which fills in all of this, and then combine them all together and use the grid of the apogee stars, which we trust more, to constrain what's going on in the H1, which gives us higher resolution. That is going to be a bear to do, but would be really cool because then you can study things like rolling motions and all sorts of cool details about flows around molecular clouds, and I mean, it can get really cool. But you have to convince yourself you can believe it.
Another real nail in the coffin of any idea about material arms would be if you can see things in old stars.
Right.
Most of what you've shown is mesas and younger stars.
Yeah.
Have people ever trying to see anything in 2 mass?
Yeah.
Or
Oh god, there is a paper on this. I'm sorry, you're scratching the back of my brain. There is some paper about some mild detection of spiral structure in older stars. It does not jump out at you. It does not bite you on the butt. But there is some possibly disputed. So yes, people are interested in this, and I don't think there's a great solid detection, but please correct me if I'm wrong. I don't know that literature as well as I should.
I think we can continue this conversation with beverages and snacks. So thanks, Josh, again.
Thank you all.